On the 29th of October, 2025, an extraordinary event unfolded. The celestial wanderer designated 3IATLAS achieved its closest proximity to the Sun. During these crucial hours, it behaved in a manner utterly inconsistent with any natural comet. It amplified its luminosity by a factor of 5, not through a gradual ascent nor predictable surge, but a 5-fold increase in brilliance, casting a blazing azure against the vast expanse of the cosmos. The pertinent data collected from observatories across the globe arrived between the 31st of October and the 4th of November. Scientists rigorously verified the figures. The surge in brightness was undeniably real. However, this is what has left them perplexed. With such a dramatic increase in luminosity, 3IATLAS should have experienced a mass depletion of at least 13%. Comets intensify their glow as ice transitions to gas, as their frozen nuclei vaporize under solar warmth. Greater brilliance signifies a larger quantity of material being ejected into space. This is elementary physics. A naturally occurring comet exhibiting this magnitude of luminosity would shed an immense cloud of gas and dust, a halo observable by every telescope trained in its direction. Yet upon astronomers' search for this anticipated cloud, they encountered something profoundly unsettling. The initial imagery captured subsequent to its closest solar approach reveals no indication of the substantial gaseous envelope that ought to be present. No expansive coma, no debris field commensurate with the degree of observed brightening. If 3IATLAS adheres to the immutable laws of nature, it must have expelled 13% of its mass within a matter of days. Where has all that ejected material vanished? The mathematical calculations are straightforward. Harvard astronomer Avi Loeb meticulously computed the mass loss, applying the principle of momentum conservation. For a comet to accelerate without the influence of gravitational forces, it must propel matter in the opposing direction, akin to a rocket expelling fuel. The magnitude of force detected on 3IATLAS corresponds to a specific quantity of mass that was compelled to depart its nucleus at thermal velocities. This implies the standard evaporation of ice and gas driven by ambient temperature. In such a scenario, the comet would necessitate shedding more than 13% of its total mass. Conversely, if an alternative mechanism facilitated the acceleration, one that expelled material at significantly higher velocities, then a considerably smaller mass expenditure would be required. This presents the paradox. Either we are overlooking a colossal gas cloud that the laws of physics dictate must exist, or the acceleration originated from a source that deviates from the behavior of sublimating ice. Further adding to the enigma is a second comet bearing the Atlas designation, C2025K1 Atlas. This object, unlike the first, originates not from an alien stellar system, but from the Oort cloud situated at the outermost fringes of our solar system. It reached its perihelion 3 weeks prior on the 8th of October, plunging to within 31 million miles of the Sun. Experts had anticipated its complete disintegration. The majority of comets that undertake such an extremely close passage are fractured by the immense gravitational stresses and intense solar radiation. C2025K1 was expected to fragment into a streaking vapor and a scattering of debris. Astonishingly, it not only endured but underwent a profound transformation. Astrophotographer Dan Bartlett captured an image of it from June Lake, California. This photograph reveals a phenomenon rarely observed in the study of comets. The comet emanates a golden luminescence, not the familiar white, nor the characteristic green associated with carbon emissions, nor the blue derived from ionized gases. It possesses a golden hue, a warm metallic sheen enveloping its tail, as if the sun itself had transmuted its surface through alchemy. Comets reflect solar light via their dispersed dust particles and emit colors based on their inherent chemical composition. Green light originates from dicarbon molecules. Blue light emerges from ionized carbon monoxide. Red hues can signal the presence of organic compounds. However, the golden luminescence signifies something specific, an absence. Spectroscopic analysis conducted at the Lowell Observatory in Arizona corroborates the visual suggestion of the color. C2025 K1 Atlas exhibits a severe depletion of carbon-bearing molecules. Dicarbon, carbon monoxide, and cyanide, compounds found in virtually every known comet, are present only in trace quantities. Across the entire catalog of observed comets, only 2 others have demonstrated this level of carbon deficiency. The probability of encountering a third such object is vanishingly small. When carbon compounds are absent, the remaining dust particles reflect sunlight in a distinct manner. The consequence is that peculiar golden glow, that strange metallic radiance. Scientists openly concede their uncertainty regarding the precise reason for this comet's carbon deficiency. Logically, it should have formed from the same primordial material as other Oort cloud objects. Its composition ought to mirror that of its celestial siblings, yet it does not. Both comets bear the Atlas name. Both have defied all predictions. The interstellar visitor displayed an impossible brightening without the anticipated release of gas. The native solar system object survived a sentence of destruction and emerged with a chemically anomalous composition. The 8th of October and the 29th of October, separated by 3 weeks, marked 2 perihelia, 2 celestial bodies that refused to conform to expectations. The United States government has fallen silent. NASA's standard dissemination of data and imagery ceased with the federal shutdown that commenced on the 1st of October. The usual continuous flow of observations, the detailed reports that typically follow significant astronomical occurrences, were abruptly halted. On the 31st of October, Congresswoman Anna Paulina Luna dispatched a formal inquiry to NASA's acting administrator, demanding the disclosure of all records, images, and data pertaining to 3ATLAS. She deemed this information critical for comprehending interstellar visitors and their interactions within our solar system. NASA scheduled a teleconference with her for the 6th of November, no earlier. In the interim, the All-Domain Anomaly Resolution Office, a division within the Pentagon established to investigate unidentified phenomena, issued a statement. They affirmed they are diligently monitoring reports, but consider 3ATLAS to be outside their purview. It has been classified as a comet and therefore not an unidentified anomalous phenomenon, thus not their concern. However, if it is merely a comet, why does it contravene established models? Why does one exhibit a golden luminescence devoid of the elements that should define it? And why does the other shine 5 times brighter without dispersing the mass that physics mandates? Lowe characterizes this situation as a potential black swan event. While acknowledging it is most likely a natural phenomenon, he stresses that the observed anomalies are sufficiently significant to warrant consideration of alternative hypotheses. The ramifications, should this prove to be something other than a comet, would be profound for humanity. Between the 27th of November and the 27th of January, the International Asteroid Warning Network will conduct a focused observation campaign. Telescopes worldwide will direct their attention to 3ATLAS as it recedes from the sun, finally emerging from the blinding solar glare that has hitherto obscured it. They intend to meticulously measure its composition using spectroscopy, meticulously track any further acceleration, and diligently search for that elusive missing gas cloud. C2025 K1 Atlas will make its closest approach to Earth on the 24th of November, passing at a distance of merely 37 million miles. Even backyard telescopes will possess the capability to observe it, revealing that peculiar golden ribbon unfurling across the cosmos. 2 comets, sharing a single name, exhibiting behaviors wholly inconsistent with their presumed natures. The non-gravitational acceleration is the pivotal factor that fundamentally alters the scenario. When the most recent orbital calculations were received on the 5th of November, they definitively confirmed what had been suspected but not yet substantiated. 3IATLAS is propelling itself. Not to a significant degree, but sufficiently to be measured and to hold consequence. The acceleration can be dissected into 2 distinct components, both lying within the comet's orbital plane. There is a radial thrust directed away from the sun and a transverse force acting perpendicularly to that direction. No vertical component is present, indicating no force is acting upon the comet to push it either upwards or downwards relative to its orbital path. Instead, these two forces, precisely aligned within the orbital plane, function in a manner analogous to controlled propulsion. The measured values register at 3.7 standard deviations above the background noise. In statistical terms, this is considered robust, not overwhelming nor irrefutable, but significant enough that to dismiss it would necessitate disregarding the collected data. The acceleration has been normalized to 1 astronomical unit, the Earth-Sun distance, to account for the varying solar radiation pressure at different orbital distances. Even with this normalization, the forces remain detectable. Natural comets do exhibit non-gravitational acceleration. When ice sublimes into gas, it is ejected from the surface in jets, creating minute thrusters that nudge the nucleus in various directions. This phenomenon is anticipated and considered normal. However, these forces manifest erratically, originating from multiple vents across the comet's surface and exerting pressure in divergent directions as the comet rotates. The accelerations themselves are variable and chaotic. The behavior displayed by 3IATLAS is distinctly different. The forces maintain consistent directions. They align with the orbital geometry, and crucially, they necessitate a massive gas release to operate through natural mechanisms. Between July and September of 2025, astronomers analyzed 4,022 data points sourced from 227 observatories globally. During this 3-month period, 3IATLAS exhibited absolutely no non-gravitational acceleration. 0. The comet traversed space following trajectories dictated purely by gravity, responding solely to the sun's pull and the subtle influences of the planets. Subsequently, it approached perihelion, swung around the sun, and unexpectedly these forces emerged, something activated. The composition of the gas adds another layer of complexity. In October, spectroscopic observations revealed that 3IATLAS contains a significantly higher proportion of nickel than iron. This ratio is inverted. Every known comet, every asteroid, and indeed, every rocky celestial body within our solar system displays a greater abundance of iron compared to nickel. This is a fundamental aspect of planetary and small body formation. Iron is more prevalent in stellar nucleosynthesis. As stars forge elements and disperse them into the cosmos, they generate more iron. The material that coalesced to form our solar system 4 billion years ago possessed this identical ratio. Everything that originated here should reflect this fundamental characteristic. However, 3IATLAS does not. Its nickel-to-iron ratio bears a striking resemblance to industrially produced nickel alloys, the type that humans engineer for specific applications. These include enhanced resistance to high temperatures, superior corrosion protection, and robust structural integrity under extreme conditions. Furthermore, the nickel-to-cyanide ratio is orders of magnitude higher than observed in any other comet, including 2I Borisov, the second interstellar visitor detected in 2019. Cyanide is a common constituent of comets. It forms naturally from the interaction of carbon and nitrogen in the frigid depths of interstellar space. The presence of abundant nickel coupled with relatively little cyanide inverts the expected chemical paradigm. The water content is equally anomalous. It constitutes a mere 4% by mass. Comets are conventionally described as dirty snowballs, comprising vast agglomerations of ice interspersed with rock and dust. Water is the dominant component, the very substance that defines them as comets rather than asteroids. Yet 3IATLAS is remarkably dry. It possesses some water sufficient to confirm its outgassing activity, but nowhere near the levels typically characteristic of cometary bodies. 4% moisture content is more aligned with the composition of an asteroid. Nevertheless, it exhibits a tail and dramatically increased brightness, shedding material. The polarization measurements are unprecedented. When light scatters off a comet's dust particles, it undergoes polarization, with the electric field waves oscillating in specific orientations. The degree of polarization provides insights into the size and composition of the dust particles. Every comet observed thus far exhibits positive or mildly negative polarization, contingent upon the viewing angle. 3ATLAS, however, displays extreme negative polarization. No other celestial body exhibits this characteristic. Not 2I Borisov, nor any solar system comet documented in the catalog. The light reflecting off its dust particles is polarized in a manner that defies standard models. Scientists estimate the probability of this phenomenon occurring naturally to be less than 1%. While less than 1% does not signify impossibility, it indicates extreme rarity. And when these rare occurrences are compounded, when anomaly upon anomaly is accumulated, the collective probability diminishes further. A disproportionate amount of nickel over iron, an elevated nickel over cyanide ratio, a mere 4% water content, extreme negative polarization and absence of a discernible gas cloud despite significant brightening, and non-gravitational acceleration that only manifests at perihelion. Each of these individual anomalies could potentially be explained away through specific, albeit unusual, circumstances. However, when considered collectively, they form a discernible pattern. The trajectory of the comet presents its own unique puzzle. 3ATLAS entered the solar system on a retrograde orbit moving in the opposite direction to the planetary orbits. While not impossible for an interstellar object, its orbital plane aligns with the ecliptic, the flat disk where planets revolve, to within a mere 5 degrees. Most objects originating from random directions in interstellar space would intersect this plane at steep angles, arriving from above or below, plunging through at considerable inclinations. In contrast, 3ATLAS glides along a path nearly parallel to it. The probability of such an alignment occurring by chance is estimated at 0.2% or 1 in 500. While improbable, it is still within the realm of possibility. Its arrival timing also raises pertinent questions. The comet's trajectory brought it within tens of millions of kilometers of Mars, Venus, and Jupiter. These were not direct collision courses, but remarkably close approaches. Furthermore, its perihelion occurred precisely when Earth's position rendered direct observation impossible, with the sun obscuring our view during its critical passage. If one were to devise a trajectory for visiting the inner solar system while minimizing detection and simultaneously achieving close observations of multiple planets, this particular path would serve that purpose admirably. The probability of such a path occurring randomly is 0.0% or 1 in 20,000. Avi Loeb has been meticulously documenting these statistical anomalies since the comet's initial discovery. He prudently emphasizes that low probability alone does not definitively prove an artificial origin. Unlikely events do occur. The universe is vast, and peculiar coincidences can manifest naturally. However, he also points out that to disregard the possibility of an artificial origin requires ignoring the accumulated data. Scientific progress is advanced by thoroughly investigating all hypotheses that align with observations, not solely those that are comfortable or conventional. The forthcoming observation campaign is designed to rigorously test the hypothesis of a natural comet. If 3IATLAS is indeed a natural phenomenon, then the period following its perihelion should reveal the predicted missing gas cloud. 13% of its mass had to dissipate somewhere. The cloud should be visibly expanding, emitting light, and detectable across multiple wavelengths. Spectroscopy will serve to identify its constituent molecules, while imaging will elucidate its structural characteristics. If, however, the cloud remains absent and the observations yield no evidence of substantial outgassing commensurate with the observed brightening and acceleration, then the natural explanation will not merely be unlikely, it will be definitively invalidated. And if that occurs, what alternative explanations remain? The comparison of size offers a compelling narrative. 3IATLAS is colossal, possessing an estimated mass roughly 1 million times greater than Oumuamua, the first interstellar visitor detected in 2017. It is approximately 1,000 times more massive than 2I Borisov, and it is traversing space at a significantly higher velocity than both of them. This combination of immense size and high velocity is statistically improbable. Larger celestial bodies typically move at slower speeds. They tend to form in more stable environments, accumulating more material, and are less likely to be ejected from their home systems with extreme velocities. Smaller objects are more readily expelled. A gravitational interaction with a giant planet can easily fling a small rocky body into interstellar space at high speed. However, dislodging an object of 3 AATLAS's magnitude requires substantially more energy. The probability of an interstellar object being this massive while also moving at such a high velocity is less than 0.1%. And yet, here it is, the third interstellar object ever identified, deviating from the established pattern set by its predecessors. An additional detail embedded within observations from the Hubble Space Telescope conducted in July offers further intrigue. These images depict a teardrop-shaped structure encircling the nucleus, a shroud of dust emanating outwards from the solid core. However, they also reveal something else, an ejection pointed directly sunward. Comets do not behave in this manner. As a comet approaches the sun, solar radiation heats the side facing our star. Ice vaporizes and gas erupts, generating a jet that propels material away from the heat source, always away. The resulting gas and dust stream are directed in the path dictated by the outward pressure, meaning away from the sun. This is precisely why comet tails invariably point away from the sun, irrespective of the comet's direction of travel. But 3I/ATLAS displayed a jet aimed directly at the sun. This was not an optical illusion, nor a trick of perspective. Analysis confirmed its genuine existence. Between July and August, material was actively moving towards the sun from the comet's nucleus. While natural explanations are conceivable, comets possess complex geometries and uneven surfaces featuring cliffs and craters. A vent located on the night side could eject material that subsequently curves around the nucleus, appearing to be sunward from specific viewing angles. Rotational dynamics could also generate unusual patterns. These scenarios are not impossible, but they represent additions to an already extensive list of anomalies. Another anomaly requiring highly specific circumstances. Another coincidence. Meanwhile, C2025K1 ATLAS continues its own extraordinary performance. The golden comet, the resilient survivor, the chemically deficient anomaly. Post-perihelion, it should be fading from view. Comets typically exhibit their greatest brightness in close proximity to the sun. As they retreat into the outer solar system, their activity gradually diminishes. The surface cools, sublimation slows, and they dim. C2025K has reached magnitude 9, matching 3I/ATLAS in apparent brightness. For an object that barely survived its close solar passage, this sustained luminosity is unexpected. It is not increasing in brightness, but it is also not diminishing at the anticipated rate. Something about its interaction with solar radiation is preserving its visibility. The carbon depletion may hold the key. With fewer volatile carbon compounds available for early sublimation, perhaps the comet retains more material than initially expected. Its incandescent process is different. The solar wind gradually erodes the outer layers, but what remains reflects sunlight with remarkable efficiency. That golden dust, regardless of its precise composition, captures solar rays and commands our attention. Two comets, both observed at magnitude 9, both accessible to amateur astronomers equipped with modest telescopes. The interstellar visitor and the Oort cloud wanderer, separated by their origins, yet united by their peculiarities. Both were discovered by the same telescope network. Both defied expectations during their perihelion passages. Both brightened when they should have faded, survived when they should have perished, and displayed chemical compositions inconsistent with their supposed origins. The ATLAS telescope network was initially established with the primary objective of detecting near-Earth asteroids, objects that might pose a potential impact threat. It continuously scans the celestial sphere, identifying motion against the backdrop of fixed stars. Its purpose was not to discover interstellar objects or unusual comets, but to identify danger, and it serendipitously found these two. The timing of these discoveries is significant. C2025K1 was identified in May of 2025. 3ATLAS was discovered in July of 2025. Their perihelion dates were the 8th of October and the 29th of October, separated by a mere 3 weeks. Both were assigned the Atlas designation and emerged from the telescope network's automated detection algorithms within months of each other. While this in itself is not inherently suspicious, as the Atlas system regularly discovers celestial objects, its intended function is being fulfilled. However, the discovery of two such anomalously behaving comets in such rapid succession, both exhibiting characteristics that challenge our current understanding, and both demanding multiple explanations to fit within natural frameworks, prompts a critical question. Are we currently witnessing an unprecedented phenomenon in modern astronomical observation? A year in which the cosmos has seemingly decided to present us with cosmic puzzles rather than predictable icy bodies? Or is there a more profound underlying cause? The scientific community largely maintains a stance of caution. The majority of astronomers actively studying these objects favor naturalistic explanations. Comets are inherently complex bodies. They originate in diverse environments and undergo significant processing throughout their existence. Radiation from cosmic rays, impacts from debris, and gravitational perturbations all contribute to modifying cometary surfaces and interiors over eons. 3ATLAS, having spent countless millennia traversing interstellar space before reaching our solar system, would have been subjected to intense bombardment by cosmic rays. These high-energy particles would have irrevocably altered its chemical composition. It is therefore understandable that its appearance and composition might differ significantly from solar system comets. Similarly, C2025K1 originated from the extreme outer reaches of the solar system within the frigid, distant expanses of the Oort cloud. This environment is fundamentally different from the regions where most comets are believed to originate. It's plausible that objects originating from this zone naturally exhibit a deficiency in carbon compounds. Perhaps our observational data set is simply insufficient to encompass the full spectrum of possibilities. These arguments are reasonable. They acknowledge the observed anomalies while proposing naturalistic frameworks for their interpretation. They do not necessitate recourse to extraordinary explanations. However, these explanations are cumulative. Each individual anomaly requires its own unique set of special circumstances to be explained naturally. The comet's trajectory necessitates one explanation, its chemical composition demands another, its acceleration requires a third, and its timing suggests a fourth. When a sufficient number of these special circumstances are aggregated, the naturalistic explanation becomes so intricately complex as to rival the implausibility of alternative hypotheses. This is precisely where Abbe's characterization of a black swan event gains relevance. Scientific inquiry typically focuses on predictable occurrences, phenomena aligning with established theoretical frameworks, and observations that reinforce existing knowledge. When confronted with anomalies, the initial scientific instinct is to interpret them within current paradigms. This is a sound practice. However, there are instances when we encounter black swans, events so rare and unforeseen that they compel us to broaden our conceptual boundaries. Continental drift, for example, was a black swan, as plate tectonics contradicted the long-held geological assumption of a static Earth. Similarly, quantum mechanics, with its subatomic particles exhibiting dual wave-particle characteristics, defied classical physics, presenting another black swan. Black swans do not announce themselves. They initially appear as discrepancies, errors, or mismeasurements. It is only through the accumulation of evidence and corroboration from multiple independent observations that we recognize them as genuinely novel phenomena. The current celestial visitors, are they black swans or merely unusual white swans exhibiting peculiar traits? The observations conducted between November 27th and January 27th will provide crucial insights. Once Comet 3IATLAS fully emerges from the sun's glare and instruments can study it unimpeded, either the missing puzzle pieces will fall into place or the enigma will deepen. Comet C2025K1 approaches its closest point to Earth in 3 weeks. On November the 24th, during Thanksgiving week, this celestial spectacle, a golden ribbon in the sky, will be visible to anyone equipped with binoculars and clear skies. 2 Atlas comets, 2 distinct dates, and 2 unanswered questions. A further detail concerning 3IATLAS, largely overlooked outside specialized circles, is its trajectory, the direction from which it entered our solar system. In August of 1977, a radio telescope at Ohio State University detected a powerful, narrowly focused signal originating from space. This signal, lasting 72 seconds and possessing a strength far exceeding background noise, exhibited characteristics suggestive of an intelligent source. The astronomer analyzing the data was so astonished that they scribbled, "Wow!" in the margin of the printout. The signal never repeated. Decades of diligent searching of that same celestial region yielded no further detections. The "wow" signal originated from the vicinity of the constellation Sagittarius, near the Sagittarius-Scorpius border. Astronomers have debated its origins ever since, with potential natural explanations, including hydrogen line radiation emitted by passing comets or terrestrial interference. However, no definitive conclusion was reached. 3IATLAS arrived from a direction that aligns with the source of the "wow" signal to within 9 degrees. 9 degrees is not an exact match. It represents approximately 18 times the apparent width of the full moon, a substantial area of the sky, yet not entirely random. The probability of an interstellar object arriving from that general region by mere chance is a mere 0.6%. Does this imply a connection between 3IATLAS and the "wow" signal? Not necessarily, perhaps not even probably. However, it adds another data point to a growing list of low-probability occurrences. Individually, each anomaly might seem unremarkable, but when considered collectively, they become increasingly intriguing. If one were tasked with designing a probe for interstellar travel, what would be its essential functions? It would need to survey planets, ascertain their properties, approach closely enough for detailed data collection while avoiding destructive gravitational forces or easy detection. Such a probe would require robust construction capable of withstanding the rigors of interstellar space, utilizing materials resistant to radiation and extreme temperatures. Nickel alloys, for instance, exhibit excellent thermal stress tolerance, resist corrosion, and maintain stability across a wide temperature spectrum. It is plausible that such materials would feature in the construction of an interstellar probe dispatched by an advanced civilization. Furthermore, efficiency and resource utilization would be paramount. Transporting vast quantities of fuel across interstellar distances is impractical. Therefore, low-thrust propulsion systems like light sails or ion drives would be more sensible, activated only when necessary to conserve energy during the lengthy cruise phase. Upon approaching a target star, propulsion would be required for course corrections, orbital adjustments, and controlled maneuvers, exhibiting an acceleration pattern consistent with deliberate actions rather than random outgassing, particularly when activated near perihelion and aligned with the orbital plane. The water content is also a noteworthy factor. A probe would not necessarily be constructed entirely of ice. While some water might be present for cooling systems or as a reaction mass for thrusters, the primary components would be structural materials and instruments. A 4% water content aligns with technological considerations, whereas it is less consistent with a typical comet. This line of reasoning involves speculation, constructing a narrative from observed anomalies. Scientists are rightly cautious about such approaches, as data points suggest possibilities rather than prove hypotheses. The explanation of a natural comet remains viable for each individual observation, provided one accepts a confluence of rare circumstances. However, consider an alternative perspective. If presented with an object exhibiting all these characteristics, stripped of its context, what would be the logical conclusion? A composition rich in nickel, low in water, with minimal carbon, exhibiting extreme negative polarization, controlled acceleration appearing on a schedule, a trajectory aligned with planetary orbits, and timing that deliberately minimizes Earth observation during critical phases. Would the immediate assumption be a comet or something else entirely? The silence from governmental bodies carries more weight than initially apparent. NASA has documented thousands of comets, When noteworthy events occur, data is released, images appear on official websites, press conferences are held, and scientists provide interviews informing the public. In the case of 3IATLAS, this standard protocol has been disrupted. The shutdown provides a convenient veil, with agencies ceasing operations and data release, leading to a general acceptance of bureaucratic inefficiency as the cause rather than deliberate policy. However, Congresswoman Luna's request specifically for scientific data regarding visitors suggests an urgency that transcends routine curiosity. AARO's statement is particularly revealing in its omissions. They assert they are closely monitoring reports and assess the object as a comet, thus outside their jurisdiction, and not a UAP, unidentified aerial phenomena. Yet their close monitoring implies they are aware of the same anomalies observed by others, comprehending the statistical probabilities and their implications. To dismiss the phenomenon as a comet simply because it superficially resembles one constitutes circular reasoning when the very nature of the object is in question. The argument that investigation is unnecessary because it has been predetermined to be natural presumes the answer to the question that requires investigation. While this could be attributed to procedural caution, the slow pace of government agencies and adherence to protocols along with the genuine operational disruptions caused by the shutdown does not inherently prove a conspiracy or cover-up. Nevertheless, it underscores the increased importance of independent verification. The International Asteroid Warning Network's observation campaign assumes critical significance. Scientists operating independently of government, utilizing instruments deployed globally, can gather data that cannot be suppressed or delayed. The period between November 27th and January 27th promises answers, not conjecture, statistical arguments, or conflicting interpretations of indirect measurements. Direct observations of 3IATLAS across multiple wavelengths by diverse research teams will be pivotal. If the anticipated gas cloud materializes, if spectroscopy reveals natural cometary chemistry, and if the observed acceleration can be attributed to specific surface vents, then the natural explanation will prevail. The anomalies, while real, will be understood as explicable, advancing our knowledge of cometary diversity. However, if the gas cloud remains absent, if the acceleration persists without corresponding gas release, and if the composition remains inconsistent with natural formation, then we will confront an unprecedented situation. This would not constitute proof of artificial origin, but rather a failure of natural explanations. And when natural explanations falter, alternative hypotheses must be considered. Comet C20 Tutney 5 K1 Atlas might offer clues regarding its interstellar counterpart. Should both celestial bodies exhibit carbon depletion, unusual metal ratios, and characteristics inconsistent with typical comets, then their shared Atlas designation transcends mere coincidence, suggesting a discernible pattern. One golden comet from the fringes of our solar system, and one brilliant blue visitor from another star, both appearing within the same year, both detected by the same system, and both presenting chemistry and behavior that challenge existing models. Amateur astronomers worldwide are diligently tracking both objects, utilizing backyard telescopes, rooftop observatories, and university facilities. Hundreds of independent observers are capturing images, taking measurements, and disseminating data online, forming a decentralized network that offers resilience against information control. The gathered data exists independently of any single institution's capacity to manage it. November the 24th will be a pivotal date. As C25 K1 makes its closest approach to Earth, it will reach its peak brightness, rendering it most accessible for detailed study. If patterns emerge or new anomalies appear, the amateur network will be the first to detect them, prompting confirmation or refutation by professional instruments. At that juncture, NASA will be compelled to respond, irrespective of the ongoing shutdown. Subsequently, the scientific community will face the imperative of reconciling these observations with established theories. 20 days remain until C25 K1's close encounter, and 22 days until the intensive observation campaign for 3IATLAS commences. Within less than a month, we will ascertain whether these are extraordinary comets or something entirely different. The universe has presented us with two celestial messengers, both bearing the name Atlas. Both define our expectations, and both posing questions we are only beginning to formulate. Their message depends on our willingness to perceive it. History has instilled in us a healthy skepticism. The cosmos has previously misled us. Pulsars were initially speculated to be artificial beacons before their identification as rotating neutron stars. The Viking landers' apparent detection of life on Mars was later attributed to contamination and chemical reactions. Oumuamua fueled speculation about light sails, until its tumbling rotation and outgassing provided natural explanations for its acceleration. We have learned to refrain from leaping to extraordinary conclusions, diligently exhausting mundane explanations first. This scientific discipline serves us well, preventing the misinterpretation of ignorance as discovery in the confusion of the unknown with the unknowable. However, this same discipline can become a constraint. When confronted with genuinely unprecedented phenomena, an insistence on familiar explanations can impede recognition. The crucial question is not whether to be skeptical, but whether our skepticism aids discovery or obstructs it. These two Atlas comets place us directly at this juncture. The data is extant and the observations are factual. 3IATLAS intensified its brightness fivefold at perihelion without generating the expected gas cloud mandated by physics. It exhibits non-gravitational acceleration that manifested only when required, aligned with orbital geometry, suggesting deliberate control rather than random processes. Its composition deviates from natural ratios, revealing a higher concentration of nickel than iron and more nickel than cyanide, presenting a chemistry reminiscent of industrial alloys rather than cosmic ice. Comet C2025 K1 Atlas withstood temperatures and stresses that should have rendered it disintegrable. It transformed into something rare, something golden, and something chemically depleted in ways observed in only two other comets. It maintains its brightness when it should be fading, defying the predicted trajectory of cometary behavior. Both objects share a name, were discovered by the same system, and their timing places them in our sky within months of each other. Both exhibit anomalies that individually strain natural explanations and collectively challenge them. The natural comet hypothesis necessitates multiple improbable circumstances. Each anomaly requires its own unique, rare condition. The trajectory must have been precisely aligned, the composition processed by billions of years of radiation. The timing coincidentally synchronized. The acceleration must have originated from undetected hidden vents, and the missing gas cloud must have been overlooked by every telescope that searched for it. Each of these is individually possible, but compounding these probabilities, multiplying one rare event by another and then another, significantly diminishes the overall likelihood. At what point does the accumulation of special circumstances become less plausible than alternative explanations? This is the uncomfortable question, not whether aliens exist or have visited us, but whether our commitment to natural explanations has become so ingrained that we would disregard obvious evidence if it presented itself. If an interstellar probe were to exist, what would we anticipate observing? It would require survival during its journey, necessitating robust construction from durable materials. It would need to be energy efficient, activating propulsion only when necessary. It would survey planets, approaching them for data acquisition while minimizing detection risk. It might carry minimal volatile substances, sufficient only for thermal management and reaction mass. This description aligns more closely with 3IATLAS than with the comet hypothesis, as does C2025 K1. Perhaps C2025 K1 is precisely what it appears to be, an unusual but natural comet originating from the Oort cloud, chemically distinct from typical objects. Its ability to survive perihelion against predictions could be attributed to sheer structural integrity. Its golden hue, carbon depletion, and sustained brightness are all explicable through rare but natural processes. Alternatively, Perhaps its discovery 3 months prior to the interstellar visitor is not a mere coincidence. Perhaps the appearance of two anomalous objects sharing the ATLAS designation and defying expectations in the same year signifies something more. Perhaps one golden messenger from the edge of our solar system and one blue messenger from another star represent a pattern we're not yet prepared to recognize. And the honest answer is that we do not know. We possess data that challenges natural explanations without definitively proving artificial ones. We have anomalies that aggregate into patterns without forming concrete conclusions. We have observations that demand attention but do not yield certainty. The coming weeks will bring clarity. When C-225K1 approaches Earth on November 24th, instruments will meticulously analyze it. When the observation campaign commences on November 27th, 3IATLAS will be subjected to scrutiny by dozens of telescopes across various wavelengths. The missing gas cloud will either appear or its absence will be confirmed. The acceleration will either be traceable to natural outgassing or remain unexplained. The chemistry will either conform to cometary models or continue to defy them. At that point, we will possess more knowledge, enabling us to proceed with more refined questions. Regardless of their true nature, these objects have achieved something remarkable. They have compelled us to re-examine our assumptions, revealed the limitations of our models, and demonstrated that the universe still holds surprises. They indicate that our catalog of natural phenomena remains incomplete, and that the cosmos operates on scales, timelines, and through mechanisms we are still learning to comprehend. If they are indeed comets, extraordinary ones, then we have learned that objects from interstellar space and our Oort cloud can exhibit chemistry and behavior far more diverse than our theories predicted. We have learned that our models require updating, that edge cases exist beyond our experience, and that rare conditions yield rare results. If, however, they represent something else, something yet unnamed, then we have learned something more profound, that we're not alone in posing questions, that intelligence may manifest in unexpected forms, and that the universe encompasses not only physics and chemistry, but potentially intention and design. Both possibilities expand our understanding and challenge us to think more critically, observe more meticulously, and remain open to evidence regardless of its implications. The night sky has perpetually harbored mysteries. Ancient peoples perceived patterns in the stars and envisioned deities, while modern humans find patterns in data and posit natural processes. Both approaches strive to derive meaning from observations and explain the phenomena we witness. These two Atlas comets have presented us with new patterns for contemplation. Two objects originating from different sources, sharing an uncanny strangeness. One is golden and the other blue. One hails from the periphery of our solar system, the other from the vast expanse between stars. Both were discovered by automated systems designed to detect potential threats, and both arrived at a time when our instruments could detect them but not immediately explain them. They continue their journey through space, reflecting sunlight, carrying secrets encoded within their composition and behavior. Amateur astronomers are photographing them tonight, while professional telescopes are tracking their trajectories. Instruments are measuring their emissions, and data is continuously accumulating. In 20 days, C-225K1 will reach its closest proximity to Earth. In 22 days, the intensive study of 3IATLAS will commence. In the ensuing weeks and months, research papers will be published, debates will unfold, theories will be tested against observations, and we will draw nearer to understanding the true nature of these messengers, these heralds, these anomalies. Two comets named Atlas, two mysteries shrouded in data, two invitations to question our understanding of the universe and our place within it. The answers are forthcoming, whether we are prepared for them or not.